if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
Mystery interstellar object that was spotted by astronomers last week. It could be the oldest comet ever seen. It's only the third time that we've actually detected an object that has come from beyond our solar system.
On a calm night, a silent wanderer drifts across the canvas of our sky. Its origins unknown, its path mysterious. This is not a visitor from the familiar reaches of our own solar system, but an interstellar messenger, Comet 3I Atlas. Few discoveries have captured the collective attention of astronomers like this one. As only the third interstellar object ever detected passing through our solar system, 3I Atlas is not just a fleeting oddity, it signifies a rare opportunity for science. Here is a tangible fragment from a star system beyond the Sun's dominion. An actual piece of elsewhere now within our cosmic neighborhood. Its official designation, 3I Atlas, speaks to its exceptional story. 3I marks it as only the third confirmed interstellar visitor, following Oumuamua and Borisov. Atlas commemorates the network of telescopes that first spied its journey across the sky. With its solar approach imminent, astronomers have directed their most advanced instruments toward this enigmatic traveler, eager to learn what it reveals as it brushes past the sun. Yet the promise does not end with simple observation. NASA has harnessed the power of machine learning, providing the vast observational data on 3I/A TLAS to an artificial intelligence system developed by Google. In this new partnership between human curiosity and computing power, astronomers hope not just to see what is present, but to ask, can the unbiased focus of a neural network find patterns or clues otherwise lost to human eyes or preconceptions? As we follow this alien visitor in its passage through the solar system, what secrets will combine scientific insight, astronomical technology, and this nascent artificial intelligence to reveal about other realms and about us? The rare interstellar arrival. To appreciate the scale of this event, one must first understand what it means for an object from another system to pass through ours. For generations, every comet, every asteroid tracked by human observers could be traced to the family tree of our solar system, sediment of its formation, battered and sculpted through billions of years. That understanding altered dramatically with the arrival of the first two interstellar objects, Oumuamua in 2017 and Comet 2I/Borisov in 2019. These objects proved that the boundary between star systems is not absolute, that cosmic debris can and does cross those immense gulfs. 3I Atlas, discovered and confirmed as an interstellar comet, is thus not merely another transient point of light. It is a profound breach in the border that once seemed to divide us from the broader Milky Way. Its trajectory, rapid with a hyperbolic path, leaves no serious doubt. 3I Atlas is from deep space, charting a route no native solar system body could. Its closest approach to the Sun, its perihelion, is anticipated on October 30th, 2025. At that moment, it will pass about 1.4 astronomical units from the Sun, roughly 130 million miles, placing it between the orbits of Earth and Mars. This is not a close call in planetary terms, but in astronomical scales, it is a rare and fleeting passage. Astronomers' urgency is understandable. Interstellar objects do not linger. Once past perihelion, 3I Atlas will speed out of our solar system forever, vanishing back into the darkness between the stars. In this narrow window, every observation counts. Why is this important? Within ordinary comets, the dust, rock, and ices record clues about the early solar system, insight into its origin and evolution. 3I Atlas. These clues point elsewhere, offering direct evidence about processes around another star. Its nucleus, estimated to be comparable in size to Manhattan, contains matter shaped by wholly different formative forces. For planetary scientists, this object is not just old, but foreign in its very chemistry. Of course, time presses. The comet's sun-warmed activity, including the growth of its tail, documented with stunning clarity on August 27, 2025, provides a unique but perishable opportunity to sample materials never before touched by our sun. But extracting meaningful information from the complex, noisy data of such a transient visitor brings remarkable analytical challenges. Before we dive deeper into the science behind 3I Atlas and the cutting-edge tools being used to study it, consider subscribing to stay updated on every discovery and insight. Each observation, each data point brings us closer to understanding this interstellar traveler and future visitors like it. Now, let's move on. Sharpest eyes in the universe. In the pursuit of information, humanity's best telescopes joined the global campaign. Foremost was the Hubble Space Telescope, capable of capturing unprecedentedly sharp images of 3I Atlas and revealing intricate details of its nucleus. Through Hubble's lenses, astronomers identified not only the bare physical dimensions of the comet's heart, estimated at several kilometers across, but also subtle features in its surface and coma. The captured images concealed a trove of information, variances in brightness, signs of surface texture, and even histories of cosmic irradiation, now revealed in minute flashes of light and shade. Yet, images alone tell only part of the story. The faint spectral patterns hidden within the data offered clues to the comet's composition, its dust grains, ice, and volatile gases. Across wavelengths, from ultraviolet through visible and into infrared, astronomers looked for signatures of outgassing, those fleeting jets and plumes that can betray the presence of unusual molecules or rare volatile compounds. Crucially, understanding the behavior of 3I/ATLAS also required precise charting of its orbit. The trajectory, confirmed through repeated observation, shows that this object is certainly interstellar. But at this resolution, astronomers can probe deeper. Small deviations in its path, caused by jets of outgassing material or subtle radiation pressure, can reveal a great deal about the makeup and structure of the nucleus and about the dynamics of interstellar objects in general. Despite this extraordinary effort, the underlying challenge remained. Data volume and complexity threatened to overwhelm traditional methods. With so many variables, brightness, ejection rates, spectral features, orbital shifts, the possibility lingers that something crucial might be hidden beyond the scope of human perception or algorithmic search. This is the juncture where artificial intelligence began to play a pivotal next-generation role. NASA, Google AI, and the data fusion. NASA, steward of a vast repository of astronomical data and an array of analytical tools, recognized that the 3I Atlas dataset, bridging imaging, spectroscopy, and dynamical measurements presented a unique opportunity for machine learning. With Google's artificial intelligence, trained on the expansive back catalog of astronomical data, NASA initiated a novel probe into the data's structure. Unlike traditional algorithms, which depend on well-defined patterns or expectations, neural networks trained in this way can identify subtle or unusual correlations, potentially revealing new insights into the behavior and origin of interstellar comets. Critically, the process was systematic and grounded in well-established data handling. NASA scientists provided the AI with the full suite of observations: Hubble's sharp images, ground-based telescopic photometry, measurements of the evolving tail, detailed orbital calculations, and time-resolved outgassing events tracked as solar heating reached deeper strata in the comet's nucleus. Through repeated analysis, the AI parsed the dataset, seeking not just obvious signals, but faint, multivariate connections, coincidences in tail behavior and orbital deviations, chemical traces aligned with dynamic shifts, structural anomalies emerging only at the highest data resolutions. What emerged was striking. The neural network identified recurring structures within the ejected material, features that did not match those typical of comets formed in our solar system. The dust grains, for example, appeared coarser and more widely dispersed than expected. The spectral features pointed to a different aggregation history, possibly reflecting extremes of temperature or irradiation not common to the Kuiper belt or Oort cloud. Just as importantly, the AI flagged moments where the rate of gas release, outgassing, changed abruptly, stepping up in a pattern unlike the more predictable transitions seen in native comets. This might indicate reservoirs of volatile material, long isolated from sunlight, now being unlocked in a cascade as the comet undergoes its first and only encounter with our Sun. These insights advanced not just scientific understanding, but also reframed the way data is interpreted. Where conventional wisdom might see randomness, the AI could detect subtle regularities, opening the door to refined models of cometary evolution and helping guide new experimental directions for the coming months. The tale's secret: data reveals the unknown. The observation of a brilliant, structured tail on August 27, 2025, epitomized the investigative challenge and potential of 3I Atlas. Scientists familiar with cometary physics recognize the tail not just as spectacle, but as evidence of energetic change, a reaction to the solar environment distinct from anything previously observed. By parsing the Hubble and other multiband data through Google's neural network, researchers could trace the development and morphology of the tail with unprecedented detail. The AI measured not only the bulk ejection of dust and gas, but also looked for periodic fluctuations in emissions, searching for unsteady rhythms as solar warmth reached new layers in the nucleus. Examining the structure and velocity of particles in the comet's tail, the AI concluded that, although the composition overlapped with those of earlier interstellar visitors like Borisov, significant differences remained. Dust grains ejected by 3I Atlas were larger on average, and the distribution suggested formation in a colder or perhaps more turbulent region, a clue pointing to origins farther from a parent star or exposed to greater cosmic radiation. Of particular interest were the erratic bursts in outgassing as the comet heated. Instead of a package of steady emissions, as expected with regular solar system comets, whose repeated solar encounters even out such processes, 3I Atlas showed sudden, non-linear jumps. These stepwise shifts, paired with increases in the tail's brightness and measurable faint changes in the object's trajectory, demonstrated empirically that the comet's behavior was being shaped not just by gravity, but by the physics of previously untapped volatile materials. These findings, emerging from the AY's comprehensive review, opened new lines of inquiry. Why do interstellar objects behave so differently when exposed to the same sunlight? What can these unusual ejections teach us about the radiation history, chemical environment, and even the planetary system from which 3I/ATLAS was ejected? The specter of mini-probes. As researchers examined the dynamics of 3I Atlas, tail and coma, discussions arose regarding the fate of larger fragments ejected from the nucleus. Amidst widespread scientific debate, one analysis raised the possibility that the comet, in releasing denser chunks under stress or fracture, might send compact fragments onto their own trajectories. Public speculation quickly labeled these mini-probes a sensational frame for what would in nature be nothing more than fast-moving debris. It is important to state, with clarity, that this idea is rooted in scientific caution, not alarm. The term mini-probe here does not suggest any intent or technology. These are natural fragments, if present, propelled by the energetic forces acting within the comet. With a nucleus estimated to be the size of Manhattan, substantial chunks could, in principle, be torn free as internal pressure builds and cracks the core. Notably, the perihelion distance, 1.4 astronomical units, places 3I/ATLAS safely away from direct interaction with Earth. Yet as the AI tracked the motions of ejected materials, it noted a handful of fragments that deviated slightly from the main tail's dispersal pattern. These may reflect denser or more cohesive clumps, detached from the core through tidal forces or explosive sublimation. NASA and planetary defense teams, always alert to new classes of potential hazards, use these findings to adjust and refine models of fragment trajectories. At no point did evidence indicate a realistic threat to Earth or planets in the 2025 passage, but the exercise highlights a key principle. Interstellar objects are not passive, and their activity can seed the inner solar system with debris that merits careful monitoring and modeling. Far from being a cause for alarm, these analyses reaffirmed the diligence of scientific process. By thoroughly investigating the evolution of interstellar comets, astronomers and planetary scientists improve our readiness and understanding, preparing for future encounters regardless of their nature. Decoding the cosmic footprint. A central goal of examining 3I/ATLAS is deciphering its chemical origins. Solar system comets display well-known ratios of hydrogen, oxygen, carbon, and other elements, markers of conditions during our system's early history. In principle, an interstellar object might display different isotopic ratios, offering direct evidence of formation in an alien nebula or around a different kind of star. Through AI-assisted analysis, the dataset on 3I/ATLAS offered tantalizing hints, but not conclusive proof of such differences. Subtle variations at the edge of instrumental sensitivity suggested possible deviations in the isotopic mix of the ejected gases and dust compared to typical solar system comets. However, these findings remain at the limits of detection, highlighting both the opportunities and fundamental challenges of remote astronomical chemistry. Critically, The neural network's ability to cross-match compositional variation with changes in outgassing and trajectory allowed for a more holistic picture of the comet's evolution. Episodes where specific isotopic ratios shifted were often linked to abrupt increases in non-gravitational acceleration, showing how empirical data, once too dispersed to interpret, could now be tracked to events in real time. The portrait emerging from this work is one of complexity and difference, but not of certainty. While 3I/ATLAS stands as an ambassador from elsewhere, the fine details of its cosmic birthplace remain the subject of ongoing analysis and, in truth, may only be resolved by future generations of instruments, or perhaps by a daring close-up mission. The human element, wonder, and responsibility. One of the most striking dimensions of the 3I/ATLAS story is not the comet itself, but the way it has shaped our use of tools. The combination of astronomer insight with machine learning did not replace established science. Rather, it expanded its power, revealing new connections and patterns and drawing out unexpected features in a flood of transient data. By subjecting every assumption to scrutiny, NASA's protocols ensured that AI-derived insights stood up to verification. Where a keen human eye might miss a statistical anomaly or a buried variable, the algorithm proved relentless and impartial. Yet the ultimate interpretations, bringing caution, nuance, and context, remained the role of seasoned researchers. The arrival and study of 3I/ATLAS is therefore as much a story about our collective exploration as about any one comet. Through its fleeting visit, we are reminded that the solar system is not an isolated island, but one destination along many routes through the galaxy. Each such transient body from the reaches of interstellar space makes us aware of the wider environment we inhabit and the potential, however remote, for future encounters, both natural and artificial. For all the urgency, risk analysis, and public attention, the prevailing emotion has been wonder. Hubble's crisp images, analyzed and systematized by machine learning, but appreciated anew by scientific and public audiences, reinforce how much beauty and uncertainty remain even in the age of big data. The awakening of cosmic vision. Each pass of 3I/ATLAS near the Sun, each fresh eruption of its ancient core, challenges the limits of observation and interpretation. Through the partnership of telescope and algorithm, each extending the reach of the other, astronomers can pull subtle meaning from the random-seeming rush of cosmic events. The result is not a single discovery, but an integrated tapestry, tiny clues, unexpected dust structures, non-linear shifts in outgassing, minor orbital anomalies, faint suggestions of alien chemistry combine into a broader, richer account of what it means to witness the crossing of an interstellar wanderer. From this, a new science emerges, the machine-augmented study of such transients, preparing us not only to analyze, but someday to intercept or sample future arrivals. The next eye may offer even greater opportunities, especially if robotic or human missions can be guided by the predictive power of AI and the comprehensive maps prepared in advance by such data fusion. The study of 3I/ATLAS, then, is not about solving a singular mystery or announcing a simple headline. Rather, it is about making possible the next scientific leap, about building a discipline equipped to seize brief cosmic opportunities wherever and whenever they arise. A reflective passage among the stars. As 3I/TLAS arcs around the Sun at about 1.4 astronomical units and prepares in due course to slip back into the interstellar dark, it leaves humanity not with easy answers, but with a challenge and a gift. The challenge: to convert fleeting, chaotic, and sometimes ambiguous data into lasting insight. The gift: a data trove that, combined with newest analytical approaches, will inform the study of interstellar bodies for years to come. NASA's collaboration with Google, entrusting the largest and richest cometary dataset of its kind, in full, to advanced AI, signals a decisive step in astronomical research. Where once the sky was charted by a handful of observers, today it is mapped by eyes of glass, silicon and code, working in unison toward understanding. The detection of unusual dust behavior, the refinement of fragment tracking, and the hints of chemistry from another star all were revealed only by the fusion of human ingenuity and modern data analysis. The underlying lesson is that the universe's complexity routinely outpaces our expectations, and that every encounter, even a brief one, can push the boundaries of what is possible to know. As astronomers watch the receding tail of 3I/ATLAS and AI systems comb the last packets of raw data, the story is not of cosmic closure. Rather, it is a signal that our methods and our horizon of inquiry have evolved. The universe remains restless. Its riddles remain unsolved. But with each visitor, each crossing of orbits, each burst of light and data, humanity finds new ways to listen and to learn. As the passage of 3I/ATLAS fades back into the darkness, its greatest legacy may not be in any one measurement, but in the awakening of a new vision, a partnership between curiosity and computation, ready for whatever next emerges from the distant stars.